Hi, welcome to the introductory lesson for the wave function topic. What we're going to look at today is we're going to be able to write the sum of two different sine and cosine functions in a single form. And the one we're going to look at here is writing it in the form k cos x minus alpha, where k and alpha are constants. Okay, now what I mean by that is if I have sine x add cos x, how can I write that as a single trig function? Okay, so here we do have sine x and cos x, sine x in red, cos x in blue, and I want to know what happens when I add these two together. So here it's going to be 1 and 0, so it's still going to be at 1. Here it's adding 2, 1 over root 2's, which is 2 over root 2, so it's going to come up to here, and so on and so forth, just adding it together at every point. Now when you do that, you end up with a wave like this. Okay, now you end up with that green wave there. So there's your 1 again here, and so forth. Now, actually, this is the green wave there, just isolated away from the other two. Now you can see, hopefully quite clearly, that just is a sine or a cosine wave. It's still the same form, it's still got that kind of that shape, and it can be either, it can be sine or cosine. It's been made bigger, it's no longer at 1, it's up here. But it's constant, the maximum and the minimum are constant, and it can be a cos or a sine wave. What we're going to look at today is how to turn that into them. Okay, you can see here we've got two different ones, 3 sine x plus 4 cos x, still gives us a sine or a cosine wave. 12 sine x plus 5 cos x still gives us that sine or cosine wave. And we're going to look today at turning something that looks like this into this. Okay, and to do that, we're going to compare coefficients. Okay, so we want a cos x plus b sine x. We want that to look like k cos x minus alpha. Okay, now we're not doing any specific example here, we're just going to look at the general case. Okay, now in here, we can expand that. Okay, the k is just going to be k, but we know that cos x minus alpha gives us cos x cos alpha plus sine x sine alpha. Okay, and that's really the reason we're going to do this one first, because it's nice and easy to see because the cos's are together and it's a positive, and then just multiplying out that bracket, cos x cos alpha plus k sine x sine alpha. Okay, now then what we're going to do is we're going to compare coefficients. Okay, so in here, cos x is here and cos x is here. That means attached to this cos x is a, attached to this cos x is k cos alpha. So k cos alpha has to be equal to a. Okay, and then similarly, looking at the other one, sine x is here, sine x is here, connected to this sine x is b, connected to this sine x is k sine alpha. So k sine alpha has to be b. Okay, now if you can do that, you've already got 2 marks of every wave function question, and these questions are going to become very routine to you very quickly. Now what I'm doing here is just showing you the proof of how we're going to find these two things, how we're going to find k and how we're going to find alpha, and then I'm going to do 2 examples. It might be a bit of a longer video than intended, but I just want to be really thorough with it. Now what we're going to do here, just to prove how to get k, is we're going to do a squared plus b squared. Okay, now a squared plus b squared, that really means k cos squared, k squared cos squared alpha. In fact, I'm just going to go back and do that a bit more detailed. Sorry. Okay, so it's going to be k cos alpha squared plus k sine alpha squared. Okay, now that on there is k squared cos squared alpha plus k squared sine squared alpha. Okay, so there I can take out a common factor of k squared. And we know that cos squared alpha plus sine squared alpha is equal to 1. So really, a squared plus b squared is equal to k squared, which means that if I want to find out k, then I need to do the square root of a squared plus b squared. Okay, so very similar to Pythagoras, but this is how we're going to find out k. Whatever number is there in there, we're going to square them, add them together, and square root. Okay, the next thing we need to worry about is how to find this alpha. Now at the minute we've got two values. We've got a value for k cos alpha and a value for k sine alpha. Okay, now it's very tricky to calculate them because they're two different values. Basically, it's a simultaneous equations. But to get rid of that, what we know is that tan alpha is equal to k sine alpha over k cos alpha. And then because that is just b over a there, sorry. This can just give us the easiest trig equation to follow. Okay, now that's the proof of how we're going to find this out. And I'll give you two examples of actually how we're going to do that. Okay, but I'd maybe get this down as a note. It's definitely the title and this box at the bottom just detailing what we've done there. But if you wanted to get the proof as well, that might be nice. Okay, so I'll just go back and kind of pause over a bit so you can pause it. Okay, there's the first bit. There's the second bit. And there's the third bit. Okay, now looking at a couple of examples, we want to write 3 cos x plus 6 sin x in the form k cos x minus alpha. Okay, so this expanded really means k cos x cos alpha plus sin x sin alpha, which when you multiply out gives k cos x cos alpha plus k sin x sin alpha. Okay, now we're going to compare coefficients. Okay, and actually, just while we're doing this, there's your first mark there, just for being able to expand that. That's a scale higher, so there's your first mark. Okay, now your cos x is here, your cos x is here. So that means, just keep like that, 3 is attached to cos x there, k cos alpha is attached to cos x there, so k cos alpha has to be 3. Okay, similarly with sin x is there, sin x is there, so 6 has to equal k sine alpha. Okay, and that's your second mark there as well. Okay, so nice and easy, we're getting to the point where we're getting 2 marks straight off the bat. Now this is where what we proved in the last slide comes in useful. Okay, k, we know that k is equal to the square root of, well, it was a and b, but now it's 3 and 6. So we just take those two, 3 squared plus 6 squared. So k is equal to 36 root of 45. Okay, now to get alpha, we're going to turn it into tan. Now we know as tan is equal to sine over cos. Be careful to make sure that you include the k, because that's what we've got. We don't have sine and cos, we've got k sine and k cos. And then we're just going to substitute in again. So tan alpha is 6 over 3, which is 2, obviously. So alpha is inverse tan of 2. Now we know there can be several options here. There's 4 quadrants we can work in. Okay, firstly, we're going to look at cos and sine to see where we're working in here. So here, we're going to just use our cast diagram. Now the trick here is we could be working in 4, but because we've got values for sine and cos, we need to use that. So sine is positive. So we're going to tick everywhere that sine is positive, but also cos is positive. So we're going to tick everywhere cos is positive, and the place with 2 ticks this time is there. So we are going to just be working in that first quadrant. So it's just going to be the initial answer we get. So that's alpha is 63.4 degrees. And what I would do then, just to kind of housekeep more than anything else about admin, is I would rewrite that. Okay, so we're working with 3 cos x plus 6 sin x. 3 cos x plus 6 sin x. And that's equal to root 45 for k cos of x minus 63.4 degrees. Okay, and then just to tidy up my marks. So the first one was for up here for expanding. Second one was for getting your equivalencies down. Third one is for finding k. Fourth one's for finding alpha. If they're being very, very generous, they'll give you an extra one for the writing out of that then, but it's unlikely. Okay, so there it is, and that's what all these forms are going to take. All going to look like this. Okay, now what I'll do is I'll just give you one more example. I know it's gone on quite long, but I want to get in one with a negative as well. Okay, so what we want to do is we want to make 5 cos x minus 12 sin x look like k cos of x minus alpha, which means k cos x cos, alpha plus sin x sin alpha, and that's k cos x cos alpha plus k sin x sin alpha. Okay, so cos x is there, cos x is there, which means that k cos alpha is equal to 5. Okay, sin x is there, sin x is there, which means that k sin alpha, and this is a little bit trickier, is equal to negative 12. Okay, so negative 12 there, just because it's there, that's a plus, that's a minus. That's going to knock that out into negative 12. Okay, so k is equal to the square root of 5 squared plus negative 12 squared, which, when we do it, will give you 13. And for me to calculate alpha, tan alpha is equal to k sin alpha over k cos alpha. So tan alpha is equal to negative 12 over 5. Okay, and this is where we need to be right on top of our trig identity or our trig equations. So we're working on our cast diagram. We know that cos is positive, so we're working here and here, and we know that sin is negative, so we're working here and here. So it's going to be in the fourth quadrant this time, and we're going to just calculate our angle, the inverse tan of the positive 12 over 5. Reset that. Is 67.4 degrees. So alpha is equal to 360 subtract 67.4 degrees, which is 292.6 degrees. Okay, and then just a little bit of housekeeping at the end. 5 cos x minus 12 sin x is equal to k cos x minus alpha, so k is 13 cos x minus 292.6 degrees. Okay, let's just have a quick look at marks. It's not going to change this. 1 for the expansion, 1 for the equivalencies, 1 for k, 1 for alpha. Okay, perfect. Right, you'll get more practice of that in class. Let us know if you need any help. Cheers.